All right, so we're going to continue our discussions about solubility. And in this segment in particular, what we're going to be doing is determining whether an amount of compound will form a precipitate or not, and calculating the amount of a compound that can dissolve given the presence of other ions that are involved in the solubility product. So the two classes of problems we're going to be doing, we're again working with the same equation. We've got the KSP, which is going to be equal to the concentrations of the ions to the proper powers at equilibrium. Okay, so we'll first look at the ion product, and this is a lot like the reaction quotient. It's just another name for it, specific for KSP. So it's just the Q for the general reaction or equilibria for solubility reactions, just a different name, different branding. Example, so if we have magnesium fluoride, it reaches an equilibrium with a small amount of magnesium and fluoride ions. Then the ion product is equal to essentially the QSP, right? It's not the of magnesium 2 plus and fluorine squared at any concentration. So whatever the concentrations are, you can always define an ion product. And then, which is essentially, the KSP if those are at equilibrium. So that's the distinction. Ion product is this mathematical formula at any concentration. The KSP is the results of that mathematical formula at equilibrium, and there'll be a single value there. So the ion product is to KSP as Q is to K. So what we do to see if there's going to be precipitation or not, we just a specific version of comparing Q to KEQ. So if the ion product is above KSP, then it precipitates. It needs to move towards equilibrium by producing more of the solute. The reaction has too much ion, and that would indicate that the solution is supersaturated. Of course, if IP equals KSP, then it's in equilibrium. It's in equilibrium with the precipitate. It's exactly saturated. And if ion product is less than KSP, there's no precipitation. The solution is unsaturated. So a solution is formed by mixing 100 mils of 3.0 times 10 to the minus 3 barium chloride and 100 mils of 2.0 times 10 to the minus 3 molar sodium carbonate. Does a precipitate form? We are going to need KSPs in just a second, but we'll get those. So first, we need to go back to predicting precipitation reactions. What are the rules? Well, let's make our little chart here. This is not an ice table. This is just a chart looking at the four possibilities. So we've got barium 2 plus. We've got sodium, we've got chloride, and we've got carbonate. Okay, so barium chloride, if we follow the rules, it's chloride, it's soluble. Sodium chloride is of course soluble. Sodium carbonate, it's a group 1 metal, so it's going to be soluble. Barium carbonate, however, we can look up and we can see that it is insoluble if we follow the rules. Most carbonates are insoluble, and barium is not one of the exceptions. So that is the one that's insoluble. So we should look up its KSP. In this case, the KSP of barium carbonate is, again, I didn't give this to you, I have to look it up. It's 2.6 times 10 to the minus 9. All right, so let's figure out what the concentrations of barium and carbonate ion are. So the concentration of barium, that is going to be, well, it's the number of moles of barium over volume solution, which is 0.1 liters times 0.003 moles per liter. And the volume, it's 200 milliliters plus 200 it's 100 milliliters plus 100 milliliters, making 200 milliliters. So 0.200 liters. And that gives us 1.5 times 10 to the minus 10 to the minus 3 molar. Okay, so that's the concentration of barium in the combined solution. The concentration of carbonate is going to be just the number of moles of carbonate divided by the number of moles solution, and that is 0.1 liters times 2.0 times 10 to the minus 3 moles per liter divided by same total volume, 0.2 liters, and that ends up being 1.0 times 10 to the minus 3 molar. Okay, so the ion product going to be barium concentration times CO3 2 minus 1.5 times 10 to the negative 3 times 1.0 times 10 to the minus 3. So that is going to be 1.5 times 10 to the minus 6. And so the ion product is greater than the KSP. And so yes, it will precipitate. We'll get a precipitate. How much precipitate we'll get? It will precipitate until the the ion product drops down to the KSP. So keep precipitating until the concentrations are low enough that it will be in equilibrium.